Hello students, so today we will discuss about chemical properties of group 13. So first point, oxidation state and trend in chemical reactivity. So first element of this group is boron, and as we know it is non-metal. If we check this table, as we can see, the ionization enthalpy of boron, it is comparatively high. So usual nature of boron is to form covalent compound because ionization of boron requires comparatively high amount of energy. So that's why boron forms covalent compound. But if we compare the ionization enthalpy of aluminium, so as we can see it is considerably low than boron, and that's why aluminium is able to release electrons and it can form +3 ion. Then as we move from top to bottom, then usual behavior of a group should be decrease in ionization enthalpy, because as we move from top to bottom, sizes of atom increases, and that's why removal of electron becomes easy. But in this case, sizes are irregular. In group 13, as we already discussed in atomic radiuses, and we can see it here as well. So atomic radiuses are mentioned here, and as we can see, aluminium is comparatively larger than the gallium. Then gallium is shorter than the indium, and indium and thallium both has very less negligible difference in their atomic radius. So that's why removal of electron or ionization enthalpy trend, it is unusual. That means ionization of aluminium should be higher than gallium, but it is opposite in this case. As we can see, first ionization enthalpy, second ionization enthalpy, and third ionization enthalpy, all of these three enthalpies are higher in gallium and lower in aluminium. That's why gallium has comparatively less metallic character than aluminium. And reason aluminium is more metallic is, as we discussed earlier, poor shielding of d and f orbitals. Because of poor shielding, outermost orbital electron feels stronger attraction towards the nucleus, and that's why removal of these electron becomes difficult, and it increases ionization enthalpies. And as we move from top to bottom, because of poor shielding, s electron in this group, as we know electronic configuration is ns2 np1, so s electron of this group feels stronger attraction towards the nucleus, which creates inert pair effect. Inert pair effect, that means electron pair of s orbital behaves as inert, that means it won't participate in reaction. So that's why as we move from top to bottom, because of inert pair effect, +3 ionization or +3 oxidation state tendency decreases and +1 tendency increases. So bottom element shows +1 oxidation state rather than +3. Now if we compare +1 and +3 oxidation state, then +1 oxidation state has more ionic character than +3. That means +1 oxidation state will show ionic character and +3 oxidation state will show covalent character. Now why this happen? When two different elements are attached with each other via bond, let's say we have one metal and one non-metal element. So usually one bond requires two electrons. So all of the bonds have both type of characteristics. That means all of the ionic bonds has more or less covalent nature, and all of the covalent bonds have more or less ionic nature. If nature of bond is more than 50% ionic, then we will consider that bond as ionic bond. That means less than 50% covalent character, more than 50% ionic character, then it is considered as ionic bond. And if opposite is true, then we will consider it as a covalent bond. That means more than 50% covalent nature, less than 50% ionic nature, then it is covalent bond. And this percentage of a covalent or ionic bond depends on difference of electronegativity. As the difference of electronegativity increases, tendency of ionic bond increases, and as the electronegativity difference between two elements decreases, covalent character increases. So if we compare +1 and +3 ions, then +1 ion is more electropositive than +3 ion. Now you may ask why +1 is more ionic than +3. Reason is, as we remove the electron, nuclear charges becomes more and more dominant. That means if we talk about the aluminium, then if we compare two different oxidation states of aluminium, that means aluminium plus 1 and aluminium plus 3. Then in aluminium plus 1, we have 13 protons in the center and we have 12 electrons. In Al plus 3, we have 13 protons because number of protons do not change and only 10 electrons. So as we can see, we have higher number of protons which attracts electrons strongly. More number of protons than electron, that means higher positive charge. Higher positive charge, that means it will attract electrons strongly. Now keep in mind, oxidation state and electropositivity both are different thing. Oxidation state, that means difference of electrons and protons, whereas metallic character or electropositivity, that means tendency to attract electron. Electropositivity, that means less tendency to attract electron, and negativity, that means more tendency to attract electrons. So if we have more number of protons, it will attract electrons strongly. So same applies here. Because of less number of proton compared to electron, Al plus is more electropositive, and because of higher number of protons than the electron, Al plus 3 attracts electron strongly, which decreases its electropositivity, and that's why plus 3 ion is less electropositive than plus 1. So that means difference of electronegativity is comparatively less in plus 3 ion and it is more in plus 1. That's why plus 1 is ionic and plus 3 becomes more covalent. Now trivalent compound of this group, that means when element of group 13 is attached with three other elements. So it is electron deficient compound. If we check the electronic configuration of boron, then it is 1s2, 2s2, 2p1. That means its outermost orbit contains total 3 electron, 2 in s, 1 in p. So 2 electron of s will split and one of the s electron will jump in p electron. Now p orbital already has 1 electron and it will accept 1 electron from s orbital. So now we have 3 unpaired electrons. These 3 unpaired electrons can pair up with 3 different fluorines in Bf3 molecule, as we can see. And now we have only 6 electrons. As we can see, we have only 6 electrons and we have completely empty orbital. So because of this, these elements are electron deficient compound. That means when group 13 element forms 3 different bonds, it do not complete its octet. So that's why they are referred as electron deficient. And because of this empty orbital, these compounds behaves as Lewis acid, because Lewis acid has tendency to accept electron. So when Bf3 reacts with NH3, and we know nitrogen carries one lone pair in NH3, so lone pair of electron will be donated in empty orbital of boron, that means here. So because of donation of electron of nitrogen from NH3, we can produce Bf3 NH3 compound. As we can see, example of same is mentioned here. First we have one boron with 3 different attachments which has electron deficiency. That's why it can accept electron pair from the nitrogen and then it can form tetrahedral compound. Similarly, aluminium chloride achieves stability by forming dimer. That means it will exist as two different molecules behaving as single molecule. These center chlorine are referred as bridge chlorines or bridge atoms. They have bond with both of the aluminium. Although chlorine forms only single bond in normal condition, here we have 1 by 2 bonds with both of the aluminium. So if we count, total number of bondings with each aluminium is 2 permanent bondings of 2 different chlorine present at end of the molecule or dimer, and half bonds of 2 bridge atoms. That's why total number of bond per aluminium it is still 3. Similarly, if we check the bridge chlorine, then it has half bonding with one and half bonding with second aluminium. So total of bonding again 1. So it behaves normally. And this happens because of deficiency of electron in aluminium as well. Now normally these elements have only 4 orbital, 1 s orbital and 3 p orbital, and because of this element forms total 4 bonds. So usually they form tetrahedral or MOH type ions. But except boron, all the other elements of group 13 contains d orbital, which is empty. So if requirement occurs, then these elements can use d orbitals to expand their covalency. Because of that, aluminium can form multiple bonds more than usual. If this element forms only 4 bonds, then it includes one s orbital and 3 p orbital. That's why they form sp3 hybridization. But if they uses their d orbital, then they can form more than 4 bonds. As we can see, aluminium can form up to 6 bonds. So it uses its s orbital, 3p orbital, and later it can use 2 more orbital from d. That's why hybridization will be sp3d2. It uses one s, 3p, and 2 next d orbital. Now let's talk about the reactivity towards the air. As we know, nitrogen and oxygen, these are two main components of air. So these elements can react with nitrogen and oxygen. Usually oxygen is more reactive, so this element can react with oxygen easily. But with nitrogen we require higher amount of energy. Boron in crystalline form, it is unreactive, but aluminium can easily react with oxygen because it is metal. So we know that oxidation of metal, that means corrosion of metal or rusting of metal. When iron comes in contact with atmospheric oxygen and moisture, it will get rusted or it will form oxide of iron. But oxide of aluminium is very strong compound. On the other hand, oxide of most of the metals are weak compound. As for example, oxide of iron, it is very weak compound if we compare it with metal itself. So oxide of aluminium is strong, that's why it will form a protective layer on the surface of aluminium, which protects the aluminium from atmospheric attacks. You can notice when we use aluminium metal, we do not need to cover it with paint. On the other hand, for iron like metals, we have to cover it with paint, because if it comes in contact with atmospheric oxygen and moisture, it will start rusting. On the other hand, aluminium do not require this type of protection because oxide layer of aluminium protects aluminium metal. So amorphous boron and aluminium metal on heating forms B2O3 and Al2O3 respectively. That means trioxide. With nitrogen we require high amount of energy, that means high temperature, and then it can form nitride as mentioned here. Now, as we already discussed, non-metallic oxides are acidic in nature and the metal oxides are basic in nature. So, as the metallic character increases, basicity of oxides increases, and as the non-metallic character increases, acidity of elements, oxides will increase. So, based on this, we can say that boron trioxide is acidic. On the other hand, aluminium and gallium oxides are amphoteric, that means they can act as acid and base both. And indium and thallium, they are basic in their properties. Now reactivity towards acids and alkali, that means acids and base. Now boron does not react with acid or base at usual temperature, but aluminium dissolves in mineral acids and aqueous alkalis, thus shows amphoteric nature. That means it reacts with acid and base both, that's why it is amphoteric. Because with acid it can act as base and with base it can act as acid. Aluminium with HCl, it simply replaces the hydrogen because hydrogen is less metallic than aluminium. So usually aluminium will oxidize and it will form positive ion of aluminium and it will reduce the hydrogen. So that's why it will produce aluminium chloride and it releases hydrogen gas. But with nitric acid it does not give any kind of reaction. because nitric acid is oxidizing agent. Because of this oxidizing nature of nitric acid, it will oxidize the aluminum, which produces aluminum oxide on the surface of metal, and as we already discussed, aluminum oxide creates protective layer on the surface, and that's why it prevents further reaction. So because of that, it do not react with nitric acid. With base, aluminum forms these type of complex compound. As we can see, we have AlOH4, which is complex compound, and just like the acid, it releases hydrogen gas. With halogen, all of these elements forms trihalide except thallium and iodine. So simple reaction will be group 13 element with halogens forms EX3 type compound, where X represents halogen and E represents group 13 element. Now important trends and anomalous property of boron. Boron shows anomalous property, that means different type of nature from the rest of the group members because of two reasons. First reason, it has small size. Because of small size, its electronegativity is highest from the rest of the group members. And second thing, lack of d orbital. Boron has second orbit as the outermost orbit, and as we know, in second orbit we have s orbital and p orbitals only. Second orbit do not have d orbital. D orbital will start from third orbit. That's why boron has lack of d orbital, so it has limited number of orbitals to react. That's why it reacts differently. Because of small size, it is very electronegative, and because of lack of d orbital, its covalences are limited. And this implies for each and every representative elements of p block element. That means from group 13 to group 17, all of the first element has these two type of different properties than the rest of the member: small size, high electronegativity, and lack of d orbital. So that's why all of the rest of the members can form both type of compounds, that means 4 covalency and 6 covalency, except boron, because for 6 covalency we need help of d orbital, which is not present in boron, and same points are mentioned in this description as well.